Hello, ladies and gentlemen. This is Alice Zhang in Peking University. Now I'm really warmly welcome you get on ICANX. This talk was started 2 years ago, and now it's already getting many people on the stage every Friday. This is Alice. The founder of this ICANX, and now today is really interesting and special day because we welcome our new speakers, and this month on the spring we have six speakers, and today we have Fu Lan from Australian National University. And she is special because now she is my colleague. I can ask. I was really happy to have Fu Lan working together since this year. This January, Lan already be our co-moderator, and it take a lot of job and help us to make ICANX more qualified. And today we have Lan to deliver his ICANX talks. We also have a very wonderful team for the panel. We have Patrick from UK, we have Wei Da from Shanghai, we have Notion from Australia. Our team will join together Lan's show. First I introduce Fu Lan a little bit. I know many people already know Lan, and see her on the stage is a wonderful, a moderator, much better than me, very smooth. Lan was now the chair professor in Australian National University, and his specialist is for the optical electronics. He's very famous in the semiconductor area, and he has published more than 200 papers and many patents, and also 5 book chapters. And he won many honors and awards. I couldn't repeat all of them, but you should remember he was IEEE Nanotechnology Council. Now he was the chair, and he's doing a great job, and gave many plenary talks. And today his talk on the ICANN stage is going very fun, right? I saw many people was already repeat these words for the nanowires, and not only applications in the traditional field, also is fighting for the new field, the metaverse. Yeah. So Lan, stage is yours, please.
Thank you very much, Alice, for your kind introduction. It's a great pleasure for me here today, actually sitting in the chair as a presenter to talk about our work at the Australian National University in study and developing semiconductor nanowires and study their application for optoelectronics integration, which has a great we see a great potential for the very important emerging technology in developing the metaverse in the coming years. So just a little bit the introduction of the place I work at, which is the Australian National University. Australian National University is actually located in Canberra, which is the capital city of Australia. So it is actually really man-made city that's located between Sydney and Melbourne. And the Canberra is actually quite small city. It's only about 400,000 population, and it's very spacious, and it's called a bush capital, so it has a lot of nice national reserves. And this image actually is taken outside. You can see many complex office building, and indeed, if you actually driving in the morning, or if you drive at evening time along Canberra, it's not actually difficult to see kangaroos in some open areas. It's really nice in this sense. And ANU is one of the top ranked universities in Australia. It's also quite well known at world. It is started in 1946, and it is actually the only one university that's funded by the Australian federal government. And ANU is actually quite a small city in terms of student numbers and the teaching. However, it's a very research intensive. So as you can see from the data from 2018, we have got about 25,000 student number, but half of them actually are postgraduate students. And also ANU is one of the most international university, has about many overseas students from about 100 countries. So it's really multicultural university. And our group is located in the Research School of Physics of ANU. So our group is called Semiconductor, Optoelectronics and Nanotechnology Group. So we've got name of Nano Opto here. And our group's mainly working using this technique called metal organic chemical vapor deposition technique to epitaxial grow compound semiconductor, mainly 3-5 materials and devices based on low dimensional structures like quantum wells, quantum dots, and nanowires, as we're going to talk about today. And we not only study the synthesis of this kind of material, we also look at fabricate them into a variety of devices for optoelectronics and energy and sensing applications. So today I'll be mainly talk about optoelectronic applications like LEDs, photodetector, because they're more relevant to photonic optoelectronic integration. I'll touch a little bit about solar cells and also some recent work in sensing as well. And this is our group at the ANU. So you can see it's also, we've got many students from all around the world. And before I actually go to talk our research, I would like to first acknowledge my past and present students and colleagues, as well as collaborators from both within Australia as well as around the world that contribute to this work I'm talking about today, and also the technical support from many colleagues from the Australian National Fabrication Facility, as well as the funding agencies that support this work. So at first, I'll have really briefly introduce you what is the 3-5 compound semiconductor. So it's very easy for a 3-5 compound semiconductor. Basically is composed by group 3 and group 5 atoms from the periodic table. And as you can see that group 3-5 semiconductors actually mainly composed from nitride-based material or arsenic and arsenide and phosphide-based material. And it's actually covering a broad range of the spectrum from UV all the way to mid infrared. So it has you can see that by tuning the different composition of the alloys, you can really cover a very broad range of wavelengths, which is very important for optoelectronic applications. And also very importantly is that 3-5 semiconductor is actually, most of them are direct bandgap semiconductors. So these have a very unique advantage compared to the indirect bandgap semiconductors, such as silicon. So that's why they are very special for optoelectronic applications, because silicon can never make good laser and LEDs because of their indirect bandgap. And also the carrier mobilities in 3-5 semiconductors also very high, so which make them very good for some high frequency devices as well. So optoelectronics based on made from 3-5 semiconductors is actually you're very familiar with them. So give you some example. For instance, the LEDs are used in the big display in your different little electronics, as well as the laser pointer we use and the laser used for fiber communications, are all made from 3-5 semiconductors. And in terms of photodetectors, a lot of you may have already used like InGas photodiode, which is very sensitive for a lot of spectroscopy studies, and some thermal imaging camera that's actually made from gallium arsenide based materials. And also, of course, you probably all know that silicon, the most efficient solar cells actually made from 3-5. So they are triple junction solar cells with efficiency up to 47%. Then they are also very great for be used as a concentrator PV because of their high efficiency. So 3-5 semiconductors really, really good for 3-5 for optoelectronics. More importantly, nowadays with the fast progressing of the technology, we are more and more using highly integrated functional optoelectronic systems. So give you a few examples. We know that optical interconnects. There's actually also integration of really different components of optoelectronics in that to transmit a signal. And the LiDAR system, which has been really developed for remote sensing, autonomous vehicles, also even in the smartphones, you have this light detection and ranging technologies, basically also, again, integration of photodetectors, lasers, different components all together, where you really need those very efficient 3.5 semiconductors over there. And more importantly, of course, we know that we're all nowadays looking into, the new AR, VR hologram system, because that composes our next sort of it becomes not only just scientific fiction, now it becomes a reality. And the people really, really looking at using all this technology to build a metaverse, right? So, the development of this technology really relied on the generation, manipulation, and detection of light. So that's what we're working with and trying to really develop systems that be able to do that. So if you look at the global optoelectronics market, it's really has a very, very fast progressing trajectory, and they predicted that annual growth of 12% through the forecast period until 2023. So that's the data I've get from the internet. So it's a multi-billion-dollar market. And however, if you look at electronic integration versus photonics, optoelectronic integration, this is a very you can see a slightly different trend. We all know about the Moore's law, basically says that the number of transistors and microchips doubles every 2 years. And indeed, that follows very well if you look at, from early 1970s always all the way to 2020. And of course, nowadays, we know that we can have billions of transistors integrated on one chip. However, if you look at the relatively, new area of photonic integration, is the Moore's law here, you can see very clearly it's much slow. We have the technology just takes off from 1990s, and up to now, there's only about thousands of components we can really integrate it to the chip. So there are all different reasons for that, but one of challenge is actually because if you look at the photonic integrated circuits where we want to integrate all the function of light generation, transmission, detection into the same chip, we basically have to go through, epitaxial growth, integration, etching, regrowth, of all these different components onto the same chip. So then you can really making lasers, amplifiers, detector modulators over there. However, this process, this kind of approach based on planar epitaxial and etching often quite challenging, especially if you have to do many regrowth process that gives a lot of complexity and also have a lot of issue with material properties. Thereby, we have to look at different alternative platform, and one of the platform is really we are working at is 3.5 semiconductor nanowires, where I hopefully through this talk will give you some feeling of how they could be quite promising building blocks for this optoelectronic photonic integration, because their versatility, the flexibility, and also the nano size. So what is so in this talk, of course, I will first give you a very brief introduction on what is 3.5 semiconductor nanowires and why we're interested in it, what kind of unique properties they have, and then I will actually using a platform which is quantum well nanowires arrays, which developed like we've been working with in the past 5-6 years. I want to use this platform to actually give you some impression of opportunities as well as the challenges we're facing to develop devices that are based on this nanowire arrays. And then if I do have time, I also want to give you some introduction of our recent work that in using another technique as top-down technique to make nanowire arrays, and show that there's also different ways to make them, also use them for different applications. So I'll talk about nanowire arrays for detector and LED applications in this talk, basically. So what is the nanowires? Nanowires basically just a nanostructure, one-dimensional nanostructure, which is typically have diameter of tens of nanometers or 100 nanometers, and then with a height about a few microns to tens of microns. So because of this very, very unique one-dimensional structure, it has a lot of interesting properties from both fundamental point of view as well as application point of view. So for example, because of this one-dimensional structure, it actually can really relax the fundamental limitation of the lattice match for material growth. So thereby, when we actually trying to grow material onto a substrate which has different lattice constants, and then because of this one-dimensional structure, it can actually relax the strain that in the lateral direction, thereby allow you to actually grow different material with large lattice mismatch. For instance, if you want to grow 3-5 on silicon, this kind of nanowire make it actually much easier compared to planar structure. And also, again, because of this unique one-dimensional nano scale, it actually can support both localized resonance and also guiding modes, thereby to modify this local density of optical states. And this can be really used to enhance the emission efficiency and as well as the directionality of the lasers and LEDs. And also at the same time, we can also use that to enhance the light absorption in both photo detectors and the solar cells. And also, as you can see that certainly with this one-dimensional 3D sort of structure, nanowire has very large surface area. So obviously large surface area is very useful for devices such as sensors and photoelectrochemical devices. Also, in nanowires, we can actually create heterostructures such as PN junctions in both this axial direction as well as the radial direction, which means actually give you a lot of flexibility to really engineering the device properties. For instance, you can decouple the light absorption from the carrier selection, carrier transport separation and transport. So they can be really useful for photodetector and solar cell applications. And of course, when you make nanowire, sometimes it create a lot of interesting fancy structures in three-dimensional, and they can also potentially be used different applications such as sensing and photo catalyst and all these applications. So a lot of interesting properties that we can really explore and for different applications. There are mainly two different ways, so a few different ways to actually synthesize or fabricate nanowires. So when one of the technique I will be mainly talk about today is about epitaxial bottom-up technique. There are two different ways to making nanowire mechanism, basically to grow nanowires. One is based on this so-called vapor liquid solid technique, where you basically spray some metal nanoparticles on the surface of your substrate, and this metal nanoparticles becomes a little seed or catalyst to really promote this one-dimensional structure. And of course, you can do some nanolithography technique and then to really making some metal discs such as gold discs on the substrate. Thereby, you can actually grow also very highly sort of ordered nanowire array. However, this technique, of course, involves some metal. Sometimes it's not very desirable for device applications. And then also there's also some other challenges in terms of dopant incorporation, some complexity into that. So another alternative technique to actually grow nanowire is through this so-called selective area epitaxy, which is the technique I'm mainly talking about today. So this is a template-based technique. So what you do is that in your semiconductor substrate, you can put one thin layer of oxide, such as silicon dioxide, or you can put silicon nitride, and using nanolithography technique to actually open holes on top of this oxide, and then this little holes basically can confine the growth of your nanowires. Thereby, you can create this beautiful nanowire arrays. So I'm going to talk about this today. Another technique is top-down technique, of course, using a sort of reverse process, top-down etching. You also can using this mask method to actually define the position of the nanowires and then do the top-down etching. So this is actually the nanowire array fabricating our lab using top-down etching technique. So let me first talk about the selective area epitaxy. So the system I'm going to mainly talk about today is indium phosphide, which is a very commonly used, very well-known 3-5 semiconductor, have very similar property as the gallium arsenide, but in the nanowire space, it turns out that the indium phosphide has very good surface properties. So it has actually much less surface defects compared with gallium arsenide. So for nanowire application, this is very important. So that's why we select this material system to do a lot of work. And so what we do is that, in the indium phosphide substrate, we have silicon dioxide, about 30 nanometers of silicon dioxide deposit on this indium phosphide. And then through electron beam lithography, combined with wet chemical etching or RIE, the reactive ion etching, we can really open holes with diameter from 50 nanometers all the way to, the 300 or 400 nanometers. And then we put it into the MOCVD reactor, putting the group 3 and group 5 precursors to promote the nanowire growth. Of course, we have to really understand the growth and to control the growth temperature, gas flow rate, and also the pressure in the system. Group 5 and group 3 material ratio, they're all very important parameters to really to understand, optimize, to really to grow nanowires. So after growth of the nanowire, certainly we do some material characterization. So this is a typical sort of indium phosphide nanowire array growing in our lab. So with nanowires, there's two types of device you actually can make in terms of their structure, right? So one is that we can actually transfer the nanowire to a substrate, such as, a silicon dioxide down silicon substrate, and then we can actually making electrical contact on that, then making them into optoelectronic devices such as lasers, LEDs, photodetectors. Another way, so this is a single nanowire device. So obviously, you can see, single nanowire with nano size. There's a lot of interesting property to study. On the other hand, we also can make them as a nanowire array device, where we're actually using some polymer to planarize the structure. And then we actually can expose the tip of the nanowire to make top contact. And on the back of the substrate, we can use make bottom contact and make them into an array device. So in our work, in our group, we do work on both because we see they all have different interesting aspects as well as applications. So my talk today will be mainly talk about array, but I'll give a very quick sort of overview of the work we also done in the single nanowire space. So one type of the device we're actually looking at is really looking at using single nanowire as a terahertz detector. So by making some photolithography to making this bow tie type of and terahertz antenna on top of the nanowires and put it into a terahertz time domain spectroscopy system, we actually be able to see, to really look at, to see that our nanowire can work as a very nice broadband terahertz detector, which has a similar signal to noise ratio compared to the bulk indium phosphide reference detector. So just to give you a bit of background, so basically, indium phosphide is a very well-known material. A semiconductor material can be used as a terahertz detector to going through this photoconductive switch technique. So because the nanowire, although we have very small sort of volume and then that produce very low level of signal, however, because of this significant reduction of the material, actually it reduced a lot of the dark current in the system, thereby can provide a very good signal to noise ratio from this single nanowire devices. So which is very, very interesting. And then furthermore, what we did is in collaboration, of course, with Oxford University and the University of Strathclyde, our previous students, Kun Peng, who did a PhD at ANU and then become postdoc at Oxford University, has developed this, fabricated this very interesting cross nanowire terahertz detector. So basically create two response channels by crossing contact nanowires on top of each other. However, of course, to avoid crosstalk, these two nanowires actually are insulated from each other. So you can see that because this antenna, perpendicular antenna's shape, it actually create this polarization sensitive detector. So of course, to fabricate these detectors is extremely challenging, and our colleagues at the University of Strathclyde has developed this transfer printing technique to be able to align the nanowire, transfer nanowire into this proper position, and then we can make contacts on that. And this is the result basically showing that the time domain terahertz response that actually at different polarization angle, showing that indeed the signal received from the two channel of the nanowire detectors really be able to actually have different response to the terahertz polarization. And then if we're using this our nanowire to detect the transmission signal from polarization sensitive material structures, where you can see that our experimental results is very consistent with the simulation results, and showing that this tiny nanowires have been very useful for actually as a terahertz polarization result to detect applications, especially with the nano size. They will be very good for the near fields of terahertz, the spectroscopy or imaging system. And also, using single nanowire, we can actually create PN junctions, right? This can be used for both solar cells, photodetector, as well as our LED application. So what we did is that we can, during our growth, we're able to put in different dopant during the nanowire growth. We can put zinc as a P-type dopant. We can put silicon as N-type dopant during the nanowire growth and create this PN junction. And then if we actually put it into SEM using a technique so-called electron beam induced current, we're able to really look at this the profile of the built-in electric field that's actually formed by having this PN junction, right? So this kind of, so this is SEM image of typical nanowire, and this is actually corresponding EB current is coming that's generated through this built-in electric field. So through this, you can really look at the doping profile in the nanowire, and then thereby use that information to feed back to the growth and our simulation and trying to optimize the device design. So this is very important for device optimization, also for solar cell device. So here is an example. We're actually showing that by using this technique, we can really change the doping profile and then achieve enhanced solar cell performance. Of course, nanowire is a good 3.5 nanowire is a great light emitter because of the unique shape of nanowire. So basically, you can see that already. You have if you transfer the break it down from substrate transfer just using a little piece of paper, you can actually break them down from the substrate and transfer into another substrate, and you can see the facet on each side of the nanowire becomes a nature sort of nice mirror facet that provide this feedback system for laser, right? So if you use optical pumping, we can really see this beautiful lasing coming from the facet, and so really showing that it's really good material for light emitting device. And of course, we want to develop electrically injected device, so we can actually also making single nanowire device like in light emitting diode, then that's actually, you can see here, we can really get quite nice electroluminescence measured from this kind of nanowire LEDs. However, if we want to make nanowire lasers, there's a much more challenging because the difficulty in making a good low loss contact and also to have sufficient gain in this kind of tiny nanoscale devices. But however, this is something we're really under work, and that's why we actually want to study first with the light emitting diode and to really understand how we can making a good light emitting device from electrical injection. Of course, as I said earlier on, I want to talk more about nanowire array. The reason, of course, not only because of fundamental reason as well as real applications. For a lot of real applications, we need to have sufficient material to have a good signal, light produced or good signal as photodetectors, as well as good reliability, and they're not fragile as a little single nanowire devices, right? And also more importantly, in the nanowire array, as I showed you before, grown by selective area epitaxy, we can really quite accurately control the nanowire geometries, such as the diameter, the height, the spacing, and the shape. So those are actually very important properties of a nanowire device, which will strongly affect its absorption or light emitting characteristics. So we really have to develop simulation technique to understand those properties and to optimize our device design. So based on that, we have actually really optimized the nanowire array design to achieve a high absorption, which can be really used for photovoltaic applications. We have also shown that by changing the diameters of nanowires, actually the light absorption resonance peak nanowire arrays can be tuned all the way from visible to infrared, near infrared. And then using this technique, we have demonstrated this multi-wavelength broadband, dual band sort of photodetectors. And also we have found that if we optimize nanowire array design, namely the diameter, the spacing, the height, as well as the fabrication parameters, the light extraction efficiency for nanowire LEDs can be increased really significantly. So apart from this optical design growth, I would also want to show you that the growth and fabrication of these electronic structures and the electrical structures in nanowires is also very important for high performance devices. So I will use this very important platform, which is called Quantum Well, to show you that how we do it. So first, why we want to do quantum wells. The quantum well is actually quite important structure for light emitting device, and I'll come back to that in a minute. But as I mentioned before, like the material system I'm talking about is indium phosphide nanowires. Everyone's very, very familiar with light emitting diode. You need to be visible, right? You want to see colors. Here, we're working with infrared. It doesn't have any colors. So, however, what I have to tell you that infrared is very important, despite you can't see them by human eyes, right? If you look at the infrared LED market, it's actually quite huge, quite big too, and there's $200 million market in 2019, and it's also have a really 10% growth predicted from 2020 to 2026. And normally infrared photo LED is being used for quite a variety of applications. A lot of them you actually been using, such as biometrics, imaging, lighting, and surveillance. Of course, as I said, when we have all this new development, the new emerging techniques, the Wi-Fi, the holography system, optical communication, as well as the Metaverse, we actually need to use a lot of infrared LEDs to transmit signal to do a lot of different things. Traditional, planar LEDs, we know that one of the big challenges because it's really the low light extraction efficiencies due to the total internal reflection effects. So normally in the planar LED, you have to create some structures to actually enhance lighting extraction. I've just mentioned that in nanowires, we actually can, by tuning the design of the nanowire geometry, array geometry, we actually can engineer and optimize the light wavelength extraction efficiency as well as the directionality. And since indium gallium arsenide, indium phosphide quantum wells being really widely using laser diode for telecommunication systems, so that's the work we actually are focusing on in our work. And of course, incorporation of quantum well is very important to further enhance light emission properties, as we very well know in the planar sort of LED and the lasers. So a bit of background about quantum well. So what is a quantum well? Quantum well is basically a semiconductor heterostructures formed by sandwiching a very thin layer of small bandgap semiconductor between this two layer of large bandgap semiconductor, thereby create a potential well, right? And then if we actually, the thin layer of semiconductor go to really very small nanometer size, you actually can have this quantum confinement effect, thereby you create the discrete energy levels within your conduction band and your valence band. And this actually, you enhance the light emission properties. So not only that, so this is, advantage. Quantum confinement can be used for, light emitting device. And as well, if you actually apply bias, you have this Stark effect where it can be used for modulators. And also, if you change the composition or the thickness of the quantum well, you actually can change the confinement energy, thereby leading to different wavelengths of the quantum well. Thereby, you can really do a lot of band gap engineering using quantum wells. So quantum wells are very important for the development of the laser technology, especially semiconductor lasers. This is why these two scientists, Alfrov and Kromer, has won the Nobel Prize in Physics in 2000 for developing semiconductor Higgs structures using high speed and optoelectronics. And they actually sharing that prize with Jack Kilby, who actually is the inventor of integrates the electronic integrated circuits. So that's really, you can see the electronic integration as well as optoelectronics is really both very important, hand in hand sort of thing. So of course, our group, we started our growth on the selective area epitaxial growth of indium phosphide. I've just shown you that before, that we have demonstrated this beautiful indium phosphide quantum nanowires based on a quite high temperature and a low 5/3 ratio growth condition. That's what we have developed in 2014. And if you look at really the TM, it really reviews this beautiful, stacking fault-free structure. So it's very high quality in indium phosphide. We have achieved the room temperature lasing from this structure. And more actually interestingly, Wuzite phase in indium phosphide, normally we don't have Wuzite phase indium phosphide as a bulk form. So, but in nanowires, you actually present this a new sort of crystal structure, which is also another quite interesting property of nanowires. So at the beginning, when we start to grow quantum wells, we think that's a beautiful system to start with, right? You have nice, good morphology, good crystal quality. We want to put, during our nanowire growth, we want to switch in this lower bandgap indium gallium arsenide to enable the formation of quantum well. So this, in terms of the process, is actually quite easy. What we do is that we can really just grow our indium phosphide nanowire at the beginning, follow the recipe we developed in the past. And then what we do next is basically switching off the precursor. So indium phosphide, we're switching back to switching to the precursor of indium gallium arsenide. And then we're just switching for a few seconds, because remember, we only need a very thin layer, nanometer scale sort of material to form a quantum well, especially this indium gallium arsenide, indium phosphide quantum well. So it's really switching back and forth precursors in the process, and we only just need a few seconds. But what we see after switching this a few seconds of indium gallium arsenide growth, is this huge different morphology we obtained after doing this indium gallium arsenide growth. And this is very interesting thing. It doesn't look very good, but it's a lot of interesting stuff to observe. So if we look at the cross section of the TM of this nanowire, you can see that we have actually we have this sort of three-dimensional quantum well sort of formed here. We have a quantum well in the actual sort of direction. We have also the radial direction quantum well, and at the corner we call it a ring quantum well. The reason we actually want to separate them is because if you look at the EDX mapping, the quantum well actually have quite different compositions, and you can see from here. So they are different quantum well, and also they have different thickness, right? So that's really just give you a very complex structure. And of course, we do a very detailed TEM analysis. What we found is that what happens that is when we grow this few seconds of indium gallium arsenide on top of our Wuzite indium phosphide structure, the growth in the radial sort of side of indium gallium arsenide somehow could very happily adopt the Wuzite structure from the core. So if you look at STM, here is all Wuzite structure, right? However, if you look at the actual quantum well component, indium gallium arsenide, somehow it tends to form a more thermodynamically favor the zinc blank structure. So if it forms a different types of, it's a cubic structure basically in zinc blend crystal. And then this is because there's a low surface energy, right? So that's how things, and then because of this different different lattice is formed, thereby leading to very different growth rate at different nanowire facets. Thereby, this gives to this different evolution of the shape on the side, and as well as the side facet growth, and very interesting nanowire morphology. So I'm not going to go to details, but if you're interested, you can see this paper that has a very nice analysis from In-Suk in this paper about the radial sort of growth evolution, how they actually transform the shape from nanogol shape. In end, it can go to a very nice hexagonal shape if you grow them if you grow multiple quantum wells. And then, of course, as I said, because of this complex structure of quantum wells, if you do, you study optical property, do a photoluminescence, you can see this position-dependent photoluminescence as we measure from the top of nanowire to the bottom of nanowire. There's a change of the peak wavelengths from, originated from the radio emission all the way to actual emission. So this is from the, to the bottom, actually, to top here, this way. So it's basically consistent with our TEM results. And of course, regardless of that not very good morphology and the shape, we are still able to put in some doping and actually fabricate into single nanowire LEDs, and somehow it works very nicely. It gives out a very nice 1.3 micron light emission as we inject current. So this is just showing that the nanowire material is really quite nice. However, we want to see how the light is really with this kind of morphology, right? We want to really see if that kind of morphology will affect our light emission, how that will affect our light extraction from nanowires, because it's very important for LED application. So we did two simulations to compare a real morphology of our growth, which is this, very inclined facet shape, a disrupted sort of, not very uniform shape. And we actually did another simulation with nanowire with this triangular shape, but very uniform length along the lens, nanowire lens. And so what we found that indeed light extraction efficiencies from these two morphology is very different. We have only just 13.5% from this nanowire with inclined facet. However, we can get 25% with triangular shape, non-inclined with no inclined facet. So that means it's very important to really create uniform nanowires to be able to achieve higher extraction efficiency. This really just be very easy to understand, because this kind of inclined lateral facet will cause this disruption of optical resonance mode and leads to a lot of optical loss through the sidewall of the nanowire. So this is not very favorable. So In-Suk, again, by really understanding that, the growth is really highly related to surface energy. So one of the way to change the energy is to change growth temperature. So he proposes two-step growth, nanowire growth, instead of using only one temperature growth, what we had before. He optimized growth and developed this two-step growth. And then to give more energy to allow the nanowires to radially evolve into triangular shape, to avoid the triangular shape rather than this all different types shape. And he's able to demonstrate a much nicer morphology with no inclined facet anymore due to the surface energy change. As you can see statistically, this two-step growth has a much better uniformity in terms of the diameter as well as the length. So after having that, he fabricated that into a nanowire device, array device, by doing planarization and contacting. And then you can see this is the cathode luminescence measurement from our nanowire, and showing very uniform emission from along the length, the whole length of the nanowire. And then the nanowire certainly works very well. And we have, again, quite nice wavelengths at about 1.3 micron. Again, we go back to see the simulation, because we know that in this inclined facet nanowire device, the simulation, actually we use the Wuzite base, which is hexagonal shape, to do simulation, and the top is actually triangular shape. But you can see that compared to the triangular shape and the hexagonal shape, the hexagonal facet actually have a higher light extraction efficiency than the triangular facet. So that is actually even also higher with the nanowires with no inclined surface. So we feel that if we can actually transform the triangular shape into hexagonal shape, we may be able further to enhance light extraction, right? So that's something also quite interesting, because from the growth point of view, that means if we can develop a Wuzite-based indium phosphide nanowire growth, and then that will be basic energy variable for the indium gallium arsenide who grows, which is more also wants to form zinc blend, especially on the top surface of the nanowire here, when we, in the actual basically direction here. So we really trying to see, okay, how can we actually change the growth window all the way from a Wuzite base to the zinc blend base, although they also have hexagonal shape, but you can see the facets are very different. So it turns out actually this the Japanese group has already done a very nice study in 2010, and actually demonstrate that if you change the growth temperature and 5/3 growth rate, you can really change the surface termination, also side for energy, surface energy, and then you can really transform the growth from Wuzite phase of Wuzite nanowire to zinc blend nanowire. So basically, we have to re-optimize our growth window to really achieve a Wuzite based zinc blend based indium phosphide. So we've done a bunch of growth optimization, basically trying to reduce our growth temperature and improve our growth 5/3 rate. And indeed, that's you can see that by changing using a high 5/3 ratio to lower temperature, we can optimize a very nice, nanowire morphology, right? And then if you look at the TM that reviews that our nanowire is actually a mixed phase, not a pure zinc blend base, but it is mixed phase. We have a lot of zinc blend segment, which is good enough to form the base for nanowire for quantum well growth. And of course, if you look at the PL, it shows it's not only a broad peak, rather it has quite a few different components, basically coming from the zinc blend segment, from the Wuzite segment, as well as the zinc blend Wuzite sort of transition as well. However, it doesn't affect actually the very important quality of our nanowire. So if we look at a minority carrier lifetime, our nanowire still have a nanoseconds level on the minority carrier lifetime, which is very similar to our Wuzite-based stacking fault-free nanowire. So very good indication for device. But more importantly, based on that, we are able to really incorporate multiple nanowire up to multiple quantum well nanowire growth. So we have used this zinc blend-based indium phosphide nanowire. We're able to grow up to 40 quantum well inside our nanowire. So this is very important for optoelectronics, right? So because quantum wells are so thin, so you really need to build enough volume. So for lasers, the gain medium, and for the photodetectors, absorption volume, so that you can really achieve higher device performance. So this basically showing that we're able to really grow many, this is 20 quantum well inside a nanowires. And if you look at the cathode luminescence, you can see that we have very uniform light emission from along the whole length of the nanowire. So that's really showing that using this facet engineering technique, we're able to demonstrate multi-quantum well growth based on zinc blend nanowire. And of course, we want to see whether the optical quality is good. So from one single nanowire device, we actually show that by doing optical pumping, we also can have a good light emission from our quantum well. So the 1.3 micron definitely is coming from the quantum well, not indium phosphide. And then it has quite nice sort of shape showing the optical pumping lasing from our quantum well nanowires. And then, of course, we want to see whether they can be made as LEDs. So we're putting the doping in the nanowire and then making it a PN junction. And indeed, we've got quite nice light emission from our nanowire in zinc blend-based quantum well nanowires. And if you look at the electroluminescence, you can see the nice increasing of the intensity with the injection of the more injection of the current. And more importantly, we've got a much higher improved output power with this nanowire array. I remember before when we have this triangular shaped, uniform two-step growth, we can only get about 2.5 micron volts from our triangular shaped nanowires. However, in this hexagonal based nanowires, we actually can get about 10 times more intensity from those nanowire arrays. So it's still not good enough, but we believe there's a few ways we can actually improve the device and to have higher sort of light output power. So if we look at the modulation speed, because it's very important for a lot of, if you want to use it for communication, for Wi-Fi, those kind of application, you need to have a high modulation speed. And our nanowire is actually quite good. It has we have shown the gigahertz modulation for our nanowire LEDs. And more importantly, if we actually able to make from the same fabrication growth, we can design nanowire array with different pitch. So we change the spacing between single nanowires. We actually, because of the changing of the pitch, the growth rate is actually different. Thereby we create nanowires, quantum wells inside nanowire with maybe like different thickness or different composition. Thereby we're able to see this big tunability of the wavelengths from 1.4 micron all the way to 1.7 micron, basically showing that you can really use that create multi-wavelength LEDs, which is very important for signal transmission and as a light multi sort of wavelength light source. And certainly, there's a lot of interest in nanoscale nano LEDs because of the size as well as the other sort of important properties. So we have just do a very small use of testing that we just grow a few small number of nanowires with different design, and then indeed we can see a quite nice emission from our just a few tens of nanowire structure, showing that they can be actually making to a very small area and pixel size. And this is actually very promising for multi-wavelengths, multi-pixel individually addressable nanowire LED arrays, which probably have a lower power consumption, has a more highly highly integratable sort of applications. And of course, if we can making quantum wells, as I mentioned earlier, has another advantage is the band gap engineering, because when you incorporate the quantum well, you're basically able to change the band gap and wavelengths of the devices. And so indeed, if we actually making multiple indium gallium arsenide quantum well with indium phosphide nanowires, we're able to extend the detection wavelengths from the indium phosphide wavelengths all the way to actually infrared wavelengths. So in this case, we can really do all the way to about 1.6 micron, which is very important for many applications. We're able to show that although we only have 40 quantum wells inside this nanowires, we can achieve quite high responsivity at 1.55 nano micrometers, so which is very important for wavelengths for a lot of scientific research as well as applications. And also have shown that we're able to actually modulate the photo detector at up to 200 kilohertz. We believe there's, again, we need to optimize, the device fabrication as well as the design to enhance this response. But the 3 dB frequency is about 20 kilohertz, which is quite nice as well for a lot of applications already. So yeah, I think I do have probably about 5-6 minutes. So I'll do a little also talk about nanowire photo detection sensors by top-down etching. So as you can see, we all know as well that epitaxial growth using MOCVD is quite expensive, and it has a very big we need this really powerful machine to do those bottom-up growth. But what I'm going to show you that some nanowire device, you don't have to use this technique. Of course, some you do, but some you probably don't. We can create new structures through top-down etching technique as well. So top-down etching, indium phosphide nanowire array, what we do in our lab is we're using, again, silicon dioxide as well as nickel as the mask. And we do the, electron beam lithography to do the patterning. And then we actually do the ICP etching to create this nanowire array. So it's a very commonly used technique. And what we're actually trying to do is actually using this very interesting, the conductivity or change of the indium phosphide nanowires for the gas sensing. So one of our sort of very initial preliminary works that we create this nanowire array with different diameters and different spacings, because you can understand that with this different spacing, we change the surface area of the nanowire, and we change also the surface property of the nanowire. So what happens is that when we have gas molecules such as nitrogen oxide coming into that will absorb onto the nanowire surface, and the electrons from the nanowire actually will transfer into the to actually react with nitrogen dioxide and form nitrogen dioxide ions. And this will actually change the concentration of your carrier inside the nanowire, and then thereby to create a reduction of the current actually you measure from this nanowire. Thereby we can really, so basically it's a conductivity change due to the absorption of the gas molecules. And of course, by optimizing the nanowire array design, we actually demonstrate that, we actually demonstrate a very high performance room temperature nitrogen dioxide sensing with a limit of detection of only 3.1 ppb at room temperature. And also it has very high selectivity to this nitrogen oxide compared to other sort of commonly used gas in a lot of pollutants. So we know that nitrogen oxide is a very common, air pollutant. So to be able to sense that at room temperature and with very stable sort of performance is very important. But this gives us a very interesting direction to really look at by using this very important the surface property as well as the one-dimensional nanostructure, nano property to actually use for the gas sensing. So another example I want to show you is actually, again, top-down etched indium phosphide, and we actually form this radio heterojunction by using zinc oxide and the AZO deposition. So you can see that we use p-type doped indium phosphide and with this n-type zinc oxide to form this radio heterojunction. And this nanowire structure has been optimized with in terms of light absorption. So we actually can really reach almost over 90% of light absorption in this nanowire array with quite, you can see small volume of material. And then, if you look at the band alignment between indium phosphide and zinc oxide, so you give very nice type 2 band alignment, which is very useful for the, the solar cell application, solar cells, because it gives you very good electron transport, and then they block this majority host to diffusion in this case. And this actually leads to very high efficiency we obtain in radio junctions. This is probably, we've demonstrated 17.1% efficiency in our radio junction nanowire solar cell. So it's this is really a result of the very high absorption of the nanowire array, as well as efficient carrier collection by using these heterostructures. Using this very similar technique, it's a similar device structure actually, we actually again look at their application for photo detection. So if you look at the PN junction formed actually in this radio heterojunction, we found that extremely high electric field that's formed in a very thin sort of an interface region between the nanowire and the zinc oxide. So this turns out to be extremely useful to reduce the dark current of the structure, and this allows us to really show that we can really detect very low level of photon, which is actually a single photon level sort of photon detection we can achieve by using this structure. This is just because of this very nice sharp sort of PN junction formed at the surface of the nanowire and the zinc oxide. So it's just to show you that basically if you use the top-down etching, maybe you have a lot of etching related defects. However, because you have using some really nice device design, you are able to avoid, we're still able to actually achieve very high efficiency devices by using this technique. So of course, more I've shown you, nanowires, it's great. You have a lot of interesting properties, also potential to really achieve high performance light emitting devices as well as the light detection devices. And for us at the moment, our research interest, the focus is really working with a group of colleagues from 5 leading Australian universities to really developing the next generation miniaturized optical systems by really integrate the light generation, manipulation, detecting elements in together to really achieve high performance optical systems. So we want to really develop high efficient lasers, LEDs, and combined with matter surface to able to tune and the light propagations, their properties, and to achieve highly efficient imaging and detection of the light. Thereby, we can develop next generation holographic displays, night vision technology, wearable optical sensor, LiDAR systems, remote sensing, as well as Wi-Fi. So it's very exciting. So all these emerging technologies really will be also very important for the development of the Metaverse that we're all looking forward to in coming times. So finally, to conclude, I hope I have shown you that 3.5 semiconductor nanowires offer a great potential for a range of device applications. Highly uniform 3.5 quantum well nanowires being achieved in our work, and we think they're very promising for multi-wavelength light emitting device in a highly integrated optoelectronic and photonic systems. And we need to really understand, optimize this, from this design, from the growth, from the optical electrical properties for developing high performance nanowire-based devices, optoelectronic integrated circuits. That's really quite critical for the real Metaverse implementation or realization. So thank you very much for your attention.
Okay, great, Lan. Yeah, very, very nice talk. Enjoy a lot. Yeah. Okay. Actually, we have questions from audience more about the applications. Yeah,
Yeah.
many people want to. Is that possible? You can emphasize how to use all these fancy devices into the metaverse. Yeah. So if you can give a few words on this.
Yeah, I guess, when we talk about metaverse, it's really something you can really see the like virtual reality things, right? So that's really a lot of information is being done in this system is actually using light to transform information. And as you can see that you want to integrate in your real life, those device needs to be quite small and has a lot of functions that built into that. So it's like, electronics, it's like your mobile phone, you have millions of billions of transistors built into that. Basically, you use electrons. However, in the metaverse, a lot of the information has to be transmitted by light, where you need all this tiny device and highly integrable tiny device with a lot of dynamically controlled properties. And that's what we're actually trying to work at, right? You have to generate light. You have to be able to use some, structure such as matter surface to manipulate light, to direct the light to the positions you want to do things. And then you actually need to have also the same time detectors to be able to detect those ones. So it's really just a highly integrated system. You have to into different system, like autonomous vehicle, like self-driving car is again another example for that. You have to have a laser mounted on the top of your car and sending out signals to explore your environment. You have to detect the lights reflect back by the interaction of the laser with the environment. And then you have to have the detectors in the car to detect that. So that's really, it's already being used, but what we need to do is really make sure they are smaller, they're more efficient, and they're more sort of efficient, and they're more faster, they're not actually using less energy, right? So that's the thing we're actually looking at.
Yeah, very nice. Actually, should be low power. Yeah, so
Exactly.
another keyword saying it should be low power. Yeah. So how about one more question before we go to the panel? I want to know is it possible to be flexible?
Oh yeah, definitely. I actually really thankful this question gave me this opportunity to actually talk about that, because nanowires, they're tiny, right? So the mechanical property, they're quite easy to break. As I mentioned earlier, in fact, when we make single nanowire devices, we're actually using a very sharp sort of using a scissor to cut a single very sharp filter paper, and then we just gently touch nanowire, we can break them from substrate, transfer to another substrate. And similarly, we actually have recently developed a technique that we're able to, using some polymer to planarize the nanowires, but we can peel them off from the substrate and then make them into flexible devices. So the sensor, we recently actually demonstrated a very good, nice flexible sensor based on that.
Wow, very, very good. Really, really exciting about this. But
That's
now,
right.
recently, I
Yeah.
was care more about the flexible and the wearable sensors. Yeah.
Yeah,
Okay.
I'll be
Yeah.
more than happy to share that yeah, in the future, because we're
Thank you,
taking
Lan. Let's
that.
move on to go to the panel. We can have more of these questions. Yeah, I think all our panelists are waiting here. They are exciting too. First, let me introduce our panelist, Patrick Parkinson. He's now a superstar in UK. And he's in University of Manchester, where is my dreaming place. Because the soccer player, yeah. So he's leading big data for the nanotechnology, and he has published 70 publications. The numbers are not important. Importance is all these publications was cover several areas. Yeah, physics, chemistry, electronics, and working really disciplinary. And now he's also supervisor startup company. Yeah, looks like he has more story to share with us, Patrick. And we have our next superstar is from China, Wei Hu. Wei was a PI at the Shanghai Institute of Technical Physics, the CAS. Chinese Academy of Science. He's very, very famous because he won the title of NSF Distinguished Young Scientist Award and many other awards. And one award is very trust to me is he won the Physics Society in China Sabendong Physics award. This people is where this way is very famous, and he did a lot of work for the fabrication and categorization of infrared photodetectors and the chips. So welcome Wei to share more story on this. And we have our challengers today is a super speaker. I think because she gave a notion Nasiri, he gave us several talk on TED. Yeah, it was a TED speaker. So we all know that TED is a super kind of a stage for the speakers, and Noshin has delivered several talks on that. He's a head of a nanotech lab on the School of Engineering and Macquarie's University, and he's 2021 superstars of STEM in Australia. It was 2021 40 and 40 young superstar of Asian Australians. His research was focused on the design of nanostructures and materials. Let's welcome all our panelists on the stage. Yeah, we're looking forward. So, Nashin, are you ready or challenging?
Yeah, sure, absolutely.
Yeah, please.
Yeah, thank you so much, Lan. It was yeah, one of the best talks, to be honest, that I've listened to in recent years. Very exciting. Every paper, every topic that you discussed in this talk was, yeah, I mean, every time that you go to the next slide, I thought that this is my favorite topic, but then the next topic actually beat the previous one. So thank you so much for such an excellent and high quality research. So I'm going to just start with a question about that quantum belt devices that you talk, and you showed us a slide that you successfully could have around 40 of them in one single nanowire. Is there any limit? I'm very curious to know that what stop you from going further, like why not 60, why not 80?
Well, I think this is really coming from what we've learned from the planar device, and also the same time is that do you need that many? Of course, in a planar device, people have grown unlimited number. It depends on the system, material system. But typically, the reason we're growing multiple quantum well up to that number is really to trying to actually develop some quantum well infrared photodetectors where you have multiple quantum wells and be able to have a good absorption and to actually be able to using this inter-subband transition to detect mid-infrared to long-infrared light. But back to the question about is that possible? I would say we should be able to grow more, but this, you can see that from the cross section with the 20 quantum well samples already, because the growth calibration is very complicated. So we sort of really want to have very uniform quantum well, but as you're growing more and more in the material, the diameter becomes bigger and bigger, your nanowire becomes thinner and thinner. So we have to recalibrate the system, and then that's a lot of work. So we sort of, from the really realistic point of view, as well as application point of view, we don't need that many.
Mm-hmm. Yeah, thank you.
Yeah, so we actually just grow 440.
Yeah, sure. And in your talk, you limited your research into only two materials in this case. Like when you talk about we need to have a large band gap and a small band gap material. What we heard from you today is only limited on two materials. Is there any limitation in terms of what type of material we can choose, or this is just based on you just decided to go deeper into this?
Yes, so I think I was just tend to focus, but we actually can grow a lot more material than that. Of course, ultimately the material you're able to grow is depending on the system. So when you do this epitextural growth, you tends to really confine to a few material growing to really avoid some cross contamination issue and all this. But for typical, really, not arsenide based or phosphide based material, we can grow, there's a limited number of material we grow, but the things I haven't shown you is actually gallium arsenide. We do a lot of gallium arsenide growth in our lab. We also have a reactor doing gallium nitride growth. So based on that, you actually cover a broad range of wavelengths and applications. One of the results I show you there, actually, I didn't say, I just quickly flick through, is this multi-pixel detector, multi-wavelength detector. That's actually based on gallium arsenide and timonite, which is, again, very important material where you can really extend to short wavelengths infrared, which is very important for a lot of technology nowadays.
Sure. So I do have more questions, but I think I'm going to just give chance to other panelists to have their question. If there is more time, I come back. Yes, absolutely.
Okay. Yeah, Patrick. Yeah, please.
All right. Thank you, Fu Lan, for that really wide-ranging discussion of so many different topics, for optoelectronics. One of the things that really caught my eye was you spoke quite a lot about the application being in photonic integrated circuitry, and things where we have high density integration, perhaps of electronics with optoelectronics. So I'm wondering, today, there are different ways people want to go about this. One of them is you grow the nanowires onto silicon, and that way you integrate it. Another way is you pick and place or do flip chip, where you actually grow them separately and then combine them. What do you see as the one that will win out technologically?
Well, I would say, I think it really depends on application. I would keep it quite open rather than confined to that, but definitely industry would prefer to everything grow on silicon, right? That's really the ultimate driving force. There's a lot of driving forces, a lot of interest in the area, but over the time, we've seen a lot of nice work demonstrated by growing nanowire on silicon, and still there's a lot of effort that, including ourselves. However, I don't want to limit, that into that, because, photonic integrated circuits can be a hugely integrated light transistor, but maybe there's also area you can really have just a small chips and with a lot of integration and, with different technique. The good thing of nanowire is you can make it flexible. I think it will be some area we can explore. You could also just have a few components there to achieve some things. So yeah, I wouldn't say which one will win, but if you want to do large scale and all this, certainly you have to probably growth on silicon still is the thing that to really will attract a lot of investment and attention, and maybe make way to the large scale.
Okay, so just to follow up a tiny bit, so what is the main challenge between now and growing all of your structures on silicon?
Oh, we keep trying actually on silicon. It's actually, it's really challenging. You thought like with this lattice mismatch problem relaxed, but it's still a lot of I think challenge we've done. I think in our group we've done the gallium arsenide nanowire growth on silicon to demonstrate that. But with indium phosphide, somehow our beginning was trying to see if we want to do that, and then we sidetracked because we start to get interested in quantum wells, and then we start to really working on that. So it's just so many interesting things coming out of that. So somehow it's just like a track. The students want to have a product. They just want to say, okay, if I get a good paper out of that, let me just do that. And silicon seems to be quite hard, but we actually are still doing some. I think recently we're trying to do the ring memory growth on silicon and all this. So yeah, still we have quite a lot of interest, but I think we have got a little sidetracked by this, metal surface things. So we start to work towards that direction a little bit. But there are a lot of groups still working on that. Industry also working on that.
Okay, well, my colleague leave a message to me. It says that silicon is the only way you can survive.
Yes, I guess that's true. But luckily, as academics, we don't have to do that. But yes, I think seriously, I think, yeah, that's industry will really do everything to make silicon work. I guess, the photonic integration is coming into a very unfortunate timing, because where silicons become the dominant things, in every, industry or electronics industry. So I think there's the way the progress is slow for photonic integration. There's a bit of reasons because of that. Because the whole infrastructure are very different. It's already being dominant, and the industry doesn't have that. They just want to do it.
Okay,
right?
yeah. Okay, we can come to Wei-Da, please.
Let's give a very interesting and comprehensive great talk on the indium phosphide, indium gallium arsenide 35 nanowires. Yes, it's very interesting, and also congratulations on your recent publication of a lot of interesting works. Compared to last time you come to our labs, and a lot of interesting work published. Congratulations. And I have two questions and comment on this your works, and especially for the quantum wire using indium phosphide and indium gallium arsenide. And when you're using for the LED is very quite good, but where you manufacture for the photo detector, it seems that there's the speed of the 3 dB frequency is not very high. What's the reason? And that is that possibly due to the heterointerface or the surface of the nanowire causing this speed? And is it possible the speed can be improved after some properly treatment of this fabrication, especially for the pixel array? This is the first question.
Yeah, okay. Do you want to ask another question, or you want me to answer this first? Yeah, so I think the speed certainly can be improved, we believe, because when we do the fabrication, the RC constant and all this, really, if you want to talk about speed, that's very important, right? And this is a PIN structure, so where we also the PN junction design is also like the doping and all this is also quite important. So the field and everything needs to do the optimization. So these two things, and also I think I have to really admit that we haven't spent a lot of time to optimize the contacting those. We have ITO as the top contact. We do a quite sort of and then we've got titanium gold on the back contact, but there isn't too much optimization to really trying to do that. So I would say the capacitance of the junction needs to be optimized, the contact resistance and all this needs to optimize. So the whole structure I would say, so, in terms of device itself, we didn't do too much optimization. It's more like we focus on looking at nanowire itself there.
Anyway, it's very interesting for the photo detectors. And furthermore, if using the PRN structure, I was quite looking forward, with maybe collaboration with you to using this kind of structure to doing the avalanche for the dye.
Yeah,
it's quite interesting.
Yeah.
Now the quality must be higher demanded for this kind of avalanche. There's also decrease the defect as well as the interface traps. It's quite difficult for the avalanche, but the avalanche is quite interesting.
I'm not sure whether you have seen. There's a nice publication, Nanoletter, on the actually avalanche photo detector based on array nanowires. It has a very nice discussion there about also the potential for nanowire to be used for avalanche photo detector. So that's I think that's the only paper I know that's actually showing that nanowire working as APD in Geiger mode. The very nice thing is that it really reduced the after pulse effect over there because of the reduction of the material volume. So you basically, this avalanche event at very low light intensity only happen with you probably 1 nanowires, right? So basically, you really don't have all the other problem from above material.
Pixel is very difficult, right?
Yeah. Exactly, but so that's actually is what I'm actually working at. But still, I think one of the challenge in our case is actually the doping.
Yes, doping.
Doping is still quite challenging too, especially P-type doping is we're still facing issues to get high level P-type doping. That's prevent us to form very good, sometimes the good contact, good PN junction we need.
Okay, thank you very much. Thank you very much. Very good, nice talk.
Thank you.
Very inspiring, discussions. I think National, you still have questions. Yeah, you're safe.
Yeah, sure. So I wanted to go back to the technique that you use for these quantum wells. If I'm not wrong, you mentioned that you use the temperature around 700. Is this like for example, if you want to grow these quantum wells, there are 2 different materials. So when you are selecting these 2 different materials, is it kind of relevant to that temperature, or can you, every time that, let's say you have your first material and then that couple of seconds that you said that the new precursor is purged into the system to grow the second, let's say the small bandgap material, do you have this option of quickly adjust the temperature, or you have to choose your material based on that temperature because the temperature cannot be adjusted very frequently?
We can certainly change the temperature during the growth, but really when you grow quantum wells, it's very important interface you have to create, because that interface, if it's rough, it causes a lot of scattering and all this, so it's not good at all. So it's extremely important to have a very sharp interface. So during that growth, for our structure, we don't stop, and then because changing temperatures is not instantly. You have to wait. You change 5 degrees, you will take a little bit of time to settle down. You don't want any temperature fluctuation during the growth at the very thin layer. So that's the thing. It's more about understanding the material, the important aspect of the growth. Of course, in terms of material, it's really depending also the material, the selection of the temperature and the growth. It depends on how easy the precursors to cracking your into different atoms and all this. So that's really depends on, again, on the material growing, as well as also the property of the material. For instance, if you're growing aluminum and gallium arsenide, we tend to use quite high temperature because that will really it's very critical to the material quality. We want to have really as little oxygen as possible to be actually incorporated into the material. So it's a lot of different consideration in terms of temperature selection. Of course, you can see from our example of nanowire growth, and the temperature is very important also for the surface energy and all this, thereby that will leading to different facet forming also, and then later on the property of the material as well. Sure. Yes, very, very good question though. Yeah.
Okay, actually, I came to the last two questions I must ask because this is the first time I can act the stage. There are more female scientists than men. We
Really?
have three ladies on the
Okay.
stage. That's the first time.
Really? Oh, wow.
Yeah, except March 8th, that's a special issue
Yeah.
just for lady female scientists. This was the normal sessions. We first time has more female scientists. So I want to ask you one more question, is Lan. Could you please give some encouragement to the young scientists or the young students, the female students? Yeah, some encouragement, suggestion.
Yes, of course. I guess my comments will be applied to everyone. But anyway, particularly if you want me to say something about female students, I would say I don't see there's a difference. Like over 20 years of my academic career, I've supervised, collaborated with many female, both male and female students and colleagues. I don't see any difference in terms of ability, the potential. So I think very important things is you have to have confidence, right? You might because I think in nature we have difference. That's not problem, but we also have the different social responsibilities in a way, like when we have to have a family, when we have kids, we do need to have that break in our career, but this is not detrimental, and it's not a way that you can stop your passion and dream in a career in science. And nowadays, people understand that very important issue and are trying to support. So you should just really make use of that support to really also be able to get support from your family. That's very important as well. So when we have so I think when you think about when you at a very early stage, don't let those kind of possibility later, interruption affect your choice of your career, because I don't think that's really. It is challenge sometimes, but if you do anything else, you will have the same challenge. So I think it's nothing special of science where when we have that challenge, we just need to learn how to deal with. And also it's a very short time break in our career. And after that, you actually become better, you become stronger. And in terms of ability, this just, this no problem. I think I have a very smart female students and doing extremely well. And they're very good, also very patient, because we are, I think, I'm not saying male is not patient, but I think this is actually it's a very unique trait that a lot of female students has demonstrated. They're very patient, which patience is great, important thing for research. So I think, yeah, I really would encourage if you do, but let your passion drives you. So whatever you do, if you do science or do something else, you really need curiosity as well as passion. Otherwise, don't do it.
Okay, great. Yeah, I like that because everyone was equal, especially the female students, the girls and the boys are born as the same, right? Yeah. So same talent, just choose what you want, right? What you dream
Yeah.
it is. Yeah, just keep on going. Like Nashin, you see, yeah, he's really confident, I feel.
Yes.
Yeah. Yeah, very brave and the confidence. That's very nice. Yeah. Okay, thank you very much. Almost the time, and thank all panelists. Today is really a great panel. We discussed so many things, not only technology. Also, we can cover,
Yeah.
and of course, I thank all our, the men scientists. Yeah, the male scientists. Your support is very important too, right? Yeah. So everyone inspire each other, and we can keep on going and get more good result, more collaborations. Yeah, I love this. Okay, thank you very much. Yeah,
Thank you.
Lan. Yeah, I have this one. Sorry. Yeah, got too many stuff here. Yeah. I should deliver this certification to you on the stage, but this time it's virtually. Yeah, I will send you in the email. Thank you so much for your wonderful talk. Yeah, and
Thank you.
also, yeah, next week we'll meet you on the slide on the stage 2. Next week is your time to chair the sessions for Professor Rashid Bashir, who's from your IUC. So we see you next week. Yeah,
Yeah,
thank you very much. Yeah, so next week, and we also have one Chinese, session. As this was a Chinese session, so we'll talk about some kind of very interesting topics for Maxwell equations. Extensions. If you are interested, you can join this Chinese session on Thursday too. Also in the end of this month and April, we will have the AKX Summit online. So please, if you're interested to register for this conference, is today's show really happy, and we hope to see you next week. And then enjoy ICANX every Friday, 8 o'clock, waiting for you.